All right, it's time for us to start on our last unit. We won't be able to get through as much as we would have in a normal semester, but I do want to show you a couple of things, and these are sort of handpicked to be things that come up in other courses. I know everybody has different other courses they're taking, but I want to make sure that I'm not leaving anything out that you might see again. So the last unit is going back to the principles of integration, and this is where we kind of started our course, trying to remind ourselves of how to do basic integration and using substitution. And to this point, we've been able to do lots of integrals that came up just using those tools. What we're talking about in the third unit are some other things that we can do to evaluate integrals other than those two things. So on this handout that I have for you, this is a table from the book that just gives a summary of all of the antiderivative rules that come out of Calculus 1. Some of them look fairly obscure, but mostly these are just derivative rules written the other way around. So for example, these rules in here, these seem very specific. You know, like what are the chances that you will ever have to integrate secant times tangent? But the reason it's on the list is because in Calculus 1, you learned that the derivative of secant was secant times tangent. And so this is just the antiderivative version of that. The inverse trig functions are kind of hit or miss, whether people have gotten to them or not. We will definitely see some of those coming up here in our third unit. That very last one, the antiderivative that gives you the inverse secant formula, we can avoid it. But the derivative of inverse sine, inverse tangent, those are ones that are useful for some other for some problems. So this is kind of where we start. Notice that the version of the antiderivative formula that's given here is one that always has a parameter a in it, and so it's using this sort of basic u substitution. In all cases, you'd be doing that antiderivative using a u equals ax substitution. But this gives us the most general form of these antiderivative rules. Each one's easy to check by taking the derivative of the right side and showing that it really does give you the left side. And in all cases, the chain rule is what makes the 1 over a and the a cancel out, and gives you that formula. Anyway, so this is what we'll assume that we have in our toolbox to start with, and then we'll build on that. As this very first assignment, I want you to just do a couple of things to make sure you are doing this right and to get everybody off to a good start. But I'm going to give it a theme that rewriting the integrand is actually a very underappreciated technique of integration. And in all of the techniques that we talk about, there's going to be some kind of tool that we sort of, a crank that we turn, and it's going to turn old integrals into new integrals. And depending on the form of the new integral, sometimes it's easy and sometimes it's hard. But the main thing is that we have to practice the skill of sort of rewriting our integrand until it looks like something that we can deal with. Because when these integrals come up in the context of one of our procedures, it's kind of unlikely that it's going to come to us in exactly the form, like a textbook form, ready for one of these formulas to be plugged in. There's a good chance that we're going to have to do some algebra or something to fix it. We see that already. We've seen that already in problems like this would be an example of it, where when we had like the antiderivative of 1 over x cubed, right? That's a very easy problem to write down. It's a very simple formula, but that is not the right form for the integration rules, right? We learned that we really want to write that way. So algebraically, all we've done is just change the way we've written the integrand, but now we're super happy with this because that's just an example of the power rule. So that's a good example of what I'm talking about here. The way an integral might be written to you to look algebraically simple may not be the right way for it to be written to be integration simple. Okay, so just to practice that skill, I have a few problems here. I'll run through them, and then I have 3 I want you to do. So in this first problem, we have an integral of a product, and we have our minds could race. We could do u substitution. There's all kinds of things that could go through our head. But if we just rewrite the integrand by doing the multiplication, multiplying out, e to the x times e to the x is e to the 2x. E to the x times 1 is e to the x. And so if I just use the distributive property to distribute that multiplication through, That's the same problem. Notice I didn't do calculus yet. I just rewrote the integrand using algebra. And now this falls into the category of wherever it would be number 9 above. I'd have 1/2 e to the 2x plus e to the x plus a constant as my answer. And I don't have to do any work other than the algebra. The second problem here, same deal. When we have a division by a single letter, then we can distribute that division through. In other words, that's the same as taking the quantity x cubed minus 1 and multiplying by 1 over x. And we can distribute that multiplication through the parentheses exactly the same way we did in number 1. So for example, this would be the integral from 1 to 2, x cubed over x minus 1 over x. That division by x can be distributed across the numerator. Notice that does not work the other way around. You can't distribute, as if you had a subtraction or addition in the denominator, you'd be stuck with it. It's only because I'm dividing by a single quantity, a single number or a single variable here, that I can do that. But once I've done that, now x cubed over x is x squared. And so the antiderivative of x squared is 1/3 x cubed. Antiderivative of 1 over x is the log of absolute value of x. This is a definite integral, so instead of doing a plus c, I would evaluate it. And I'll have 8/3 minus log 2 and minus 1/3. So that's 7/3 minus log 2. The last example here is tricky because it requires that we use a trig identity. And trig identities are not nearly as familiar as like the distributive property of multiplication. But there are a couple of them that are worth knowing. And the ones that allow us to get at integral like cosine squared would be this formula for cosine of 2x. Cosine of 2x is 2 cosine squared x minus 1. That's one of our trig identities. It's called the cosine of a double angle. Another version of that that's helpful for other problems, like the one that you'll have to do, is that's the same thing as this. So cosine of 2x can be written either one of those two ways. Not too surprising since sine squared and cosine squared are related to each other, so it's not that weird that if something has, if you can write cosine of 2x in terms of cosine squared, there's another way of writing it in terms of sine squared. But both of those things are true. In this case, this is helpful because I can just turn this equation, this identity around, solve it for cosine squared. In other words, add 1 to both sides, multiply both sides by 1/2. So that's what I'll get. So cosine squared of x is 1/2 1 plus cosine 2x. So in this problem, rather than try to do any calculus at all, my first step is going to be to just change the cosine squared into 1/2 1 plus cosine 2x. It doesn't seem like, in most problems, most non-calculus problems, that seems like that would be a huge mistake. Cosine squared seems a lot simpler than this other thing, but this other thing is exactly, I have exactly those rules in my table above. So again, I'm not doing algebra for the hell of it. I'm doing rewriting the integrand so that the new integrand fits the rules that I know, not because it's simpler algebraically, but so that it fits the rules that I know. So here I would have 1/2 antiderivative. I'm just pulling that 1/2 out in front. The antiderivative of 1 is x. The antiderivative of cosine 2x is 1/2 sine 2x from the table above, plus c. So that's probably the trickiest of them to integrate something like cosine squared to cosine or sine squared. But we can do that a lot with trig functions, and it's not uncommon that a trig identity that seems to make a problem worse actually makes it better from the point of view of antiderivatives in calculus. So your assignment, you'll see on the second page of this. First of all, I have the answers to the 3 problems that I just did written up there. But then we have something called Daily Work 9. Friday will be day 9 of our whatever we're calling this pandemic quarantine. And so here are 3 problems for you to try, where we get to do a problem where you distribute a division, you get to do a problem where you just multiply something out, and you get to do a problem involving a sine squared, which would use the other identity that I showed you a minute ago. So if you can do those 3 problems and upload them, then I think we'll be off to a good start, and we'll start learning new techniques of integration starting Monday.